Hello and welcome to the 101 Earth Observation virtual lecture series. This series is delivered by the Satellite Applications Catapult in partnership with WILDLABS. This lecture is about active remote sensing application, specifically with synthetic aperture radar. Let's have before like a description of the application, a bit of overview of why do we need to use SAR. So we have seen that with optical remote sensing, we can trigger really lots of different applications. So why do we want to use SAR? Well, for a few reasons. Very often SAR is used when optical data is not available due to cloud covering. And that's a big use of it, actually. You can think to regions where, I don't know, maybe in the Amazon region, where it rains very often for several parts of the year. And if you want to do a study over there, specifically over there, we can't really use optical data because we would always see clouds. So SAR is in this case used. Actually, the second point here is also important, that very often they can be used together. So to increase the accuracy of our products, for example, land cover. Other peculiarities on optical remote sensing are written there. So penetration into canopy. So optical data would simply see the top of the canopy, while several microwaves of synthetic aperture radar can actually enter into the canopy and see the soil. So this is a an advantage of using SAR data. Another use is on deformation monitoring, such as slope stability studies. This is another advantage versus optical data. So I mentioned in the theoretical overview of SAR that there were two components of SAR images, amplitude and phase. Just looking at the phase in this case, we can study how the ground is moving with millimetric scale, as we will see later. Or we can go a bit more into physics just by looking at different properties of the signal, called polarization in this case, to study, for example, the physical composition of crops. As I explained, SAR remote sensing is actually more complex than optical remote sensing in terms of pre-processing. So there are several steps that might be needed to get this sort of products, and this sort of product it's also called very often analysis ready data, which is data that is ready to be used either to do a processing such as a land cover description, or used on its own to do classification or whatever. First application is on deformation. So you see in this figure here a colorful overview of London, where we have areas in red and areas in yellow and areas in blue. So what we are actually seeing here is the ground deformation. And while yellow it's basically a stable area, red and blue, there are areas that they move up and down, so they subside or they uplift of a few millimeters. So what we can appreciate maybe here, it's like this line that goes around the river, so this red line. So this is actually the construction of the Crossrail, so which is like an infrastructure. It's a transport mean in London, and the construction can be actually very much identified by subsidence pattern all around it. We can do this with SAR, and this is very relevant for civil engineering application, for planning or for studying construction works. Other example here, actually what we have is typically in form of single measurements, and the displacements over here are single measurements over a city in Turkey. This is coming from a study that I have personally done. So we can see measurements here of subsidence or uplifts in this specific city, which is called Rize. And let's appreciate here the values. So millimeter per year, and the values are 2 millimeter, 3 millimeter, 10 millimeters. So we are looking at that something that is really, really small. This is particularly impressive when we think that synthetic aperture radar satellites, they're actually flying at about 500 to 900 kilometers, no, far away from the Earth. And they're able to capture this information with that so small, so small values. So just millimetric values of deformation. This is quite impressive, and in this specific paper, you can see how actually you can detect cracks in the house just looking at those values. So differential settlement and so on. That's a video from the German Aerospace Center that showcase how a point cloud generation can be actually shown in 3D. So this is another mean of getting digital elevation model. So all those points that are actually properly geolocated. I have shown before how optical data in a previous video, how optical data can be used in agriculture. SAR data can be used as well in many different applications, as we see here. So from detecting the phenological stage to a mapping of crops, to studying specific components of crops such as soil moisture, the condition, leaf array index, or even getting the height of plants, as in the video shown there. So SAR is also very much used in agriculture. Another use of SAR, which is quite common, is to map flooding and also to predict flooding. So in this case, we have a map which is actually a prediction of flooding. So with areas that are at very high risk to very low risk. So flood maps and flood mapping, it's very much a SAR application. The reason behind it it's how SAR behaves with water. So water, they're mainly a mirror to SAR, because we got our signal that is like bounce the water and then bounce back. The bouncing is not directed towards the sensor, but is a sort of like it's mirrored away. Therefore, we have a very little signal for water, and it's quite easy to detect water and therefore to detect flooding. Another use of SAR data is for deforestation and forest studies. So we can see an example here of deforestation patterns from a high-resolution sensor from a commercial company called ISI, and we have two different timing and different deforestation. We see how deforestation appears as darker in this case in the SAR image. But this sort of study can be triggered with SAR data. Earth science again and volcanology is also a SAR-friendly application. We studied, for example, on deformation and looking how the ground subside over the area and related studies, or mapping of different phenomena such as mapping lava fields, mapping cauldrons in case of glaciers and so on. And finally, again, this is linked to what I mentioned before about water, ship detection. So this is another example from the German Aerospace Center, where we have like different ship which are detected with a sensor called TerraSAR X. In this case, it's another commercial sensor that delivers high resolution data. So we see how ships appear very bright in SAR images. So why? Because, as I explained before, waters appear as dark, and shape like stand out, no, in a SAR image. Therefore, their detection can be a task that can be performed with SAR images.